7.1. So we're going to be using those formulas that we used on 7.1 for like growth, decay, things like that. But if you guys recall, when we started, we didn't necessarily know how to solve a logarithm, right? So there were all these exponential functions. We were having to just put 1 in y1 and 1 in y2 in our calculator and find where they intersect, right? Well, now we know how to rewrite an exponential as a log. We know how to solve logarithms. So we're going to look at that today. So it says y equals, let me make that thinner, y equals a times b raised to the x power is the basic parent function for your exponential form. The b is considered the base, and the a is considered your initial value. Also, what we would usually call the coefficient. So it's important for you to take note, only b is being raised to that x power, right? The a is not, only b. So only your base b is being raised to the power of x. And remember yesterday, we said that you can only take the log of something positive, right? Your log could not be negative. We also said your base could not be negative, right? So keep in mind that that means your b should always be positive, because we said we can't have a negative base. All right, so just like I was saying, previously whenever we solved those equations on 7.1, we were just using our exponential form, putting it in our calculators and finding their intersection point. But now we can solve our exponential equations by using logs or logarithms. So let's take a look at an example of this. It says, assume that there are currently 673 students at MHS. If that number is increasing at a rate of 1.2% per year, when will there be 1,500 students at MHS? All right, so currently there's 673. We are increasing at a rate of 1.2%. We want to know when will there be 1,500. So our initial is 673. Our outcome is the 1,500, right? So I would write that as 1,500 is equal to the initial 673. And we're increasing, right? So remember, that was growth. That's 1 plus our rate. And what was our rate? 1.2%, which is what as a decimal? Okay. All right, and then it's being raised to the amount of time it would take for that to happen, right? So we use t to represent time. All right, so previously what we had done is we would divide both sides by 673, right? So we would go from this to 1,500 over 673 was equal to 1 plus 0.012 raised to the t, right? And that's all we were able to do because we hadn't even practiced rewriting exponential in logarithm form or vice versa, right? Okay, but now I do know how I can rewrite this as a logarithm, right? Okay, so this is my base right here, right? This 1 plus 0.012%. So I would write this as the log of my base. 1 plus 0.012, we could just go ahead and write as 1.012 because we do know how to add that pretty easily. Okay. And we're taking the log of the other side, right? So that'd be your 1,500 over 673. And remember, we set that equal to the exponent, which would be t, right? And now you don't have to put something in y1 and y2 in your calculator. You can just type this in. You're not finding an intersection point. You're just finding an actual value, right? So a little bit less trouble on your part. So if we type log base 1.012 of 1500 over 673, what do we get? Remember to put in a log of your own choice for the base. You have to go to Math A, and it lets you choose the base. Just making sure that's the right spot. So what do we get for t when we type that in our calculator?
67.
All right. So it would take 67.19 years for that to happen. Not accurate. Okay. So let's try that again. For number 2, it says you get $5,000 for graduation gifts, and you invest it in an account that earns 3.4% annual interest that is compounded monthly. When will it grow to $7,000? Okay, so now this time our outcome is $7,000 while our initial is $5,000, right? So we start out with $7,000 equals $5,000, right? Okay, and we are growing, right? So it'll be 1 plus. Now this is one of those formulas where it's compounded more often, right? They tell us how often. So remember, you put your rate over how often it's compounded. So our rate was 3.4%, which would be 0.034, right? Over, how often did they say it was compounded? Monthly, which means I'm going to put 12, right? And then remember, for your exponent, you multiply how often it's compounded by your representation of time. So 12 was how often we said it's compounded, and t is representing time. Okay? So, just like before, we would still want to go ahead and move that 5,000 over. So we'd have 7,000 over 5,000, which really is going to just simplify to 7 over 5, right? Would be equal to that 1 plus 0.034 over 12 raised to the 12t. And now I can rewrite it as a logarithm, right? Okay, so I'm going to have log of my base. My base is this part right here. Now it's not so easy to add because we got a fraction with a decimal, so we're just going to leave it exactly like that. So we're going to write our base as 1 plus 0.034 over 12. We're taking the log of 7 over 5 is what that 7,000 over 5,000 simplified to. And we set it equal to our exponent, which is 12t, right? Okay, so 2 ways you could type this in your calculator. Remember, if you just type this part in right here, you're not getting t, you're getting 12t, right? So whatever you get when you type that in, we would just need to do what? Divide it by 12. So you can either type it all in parentheses, divided by 12 all at once, or just get your solution, then divide your solution by 12. Depending on which way you do it, you might get a slightly different answer decimal-wise than your neighbor if you guys did it different ways. So I believe when we put what I circled in the calculator, we get like 118.923. Is there anybody that's put it in that got that? And that was equal to 12t, and like you guys said, from there we'd want to divide it by 12, right? So when we divide that by 12, approximately what do we get? Good.
Just restart it.
Yeah, try doing like a force reset. Okay. All All right, number 3. Number 3 says the model for the Richter scale, which rates the severity of earthquakes, is the formula R equals log of I over I sub 0, where I sub 0 is 1, and I represents the intensity of the earthquake, and R is the Richter scale value. So it's got a couple different ones for us to solve here. So it says for part A that the intensity is a 3.0 quake. So that's what it would be on the Richter scale, right? So that's what I would replace the R with in the equation. So I'd have 3 equals log. They didn't put a base, so what's the understood base? 10. So you could just use the log button on your calculator for this one, since it's an understood base 10, of the intensity over I sub 0. And they said for I sub 0, we can always just plug in 1. All right, so in this case, I would want to rewrite my log as an exponential, right? So when I rewrite, you guys said our base was 10, so I would have 10 to the third is equal to I over 1, which is really just I. So we really just have 10 to the third, right? Which is what? Okay. All right. Part B says do the exact same thing, but for an intensity of 7.0. So instead of 3.0, it's 7.0. So I should set it up the same way, right? So what's going to be the intensity for this one? Yes, I'm trying to count my zeros. Yeah, that's right. Yeah. So we'd have 10 to the 7th when we rewrite, which would be, right? Did I have the right number of zeros? 1, 2, 3. 1, 2, 3. Okay. All right. Okay, now the last one, they worded a little bit differently, right? So we're going to have something else to plug into. It says, if the intensity of the earthquake is 80,500,000, find the Richter scale value. So this time we have something to plug in for I. We're looking for R, right? So this one would look like R equals our log of our intensity which is always over 1, right? And so in this case, everything's already on one side of the equation, so I would just type this in my calculator, right? And approximately what do we get there? Depending on how far you round. Nice. Okay, just a couple more examples on the back. So if you'll flip it over on the back, they give us a formula for pH. It says the acidity or the pH model is pH equals negative log, and then we've got in brackets our H, is a measure of the hydrogen ion concentration, H, measured in moles of hydrogen per liter of solution. Find the pH of the solution, 10.3 times 10 to the negative 5th moles of H per liter. Okay, so we're going to use that formula. So we'll have that our pH is equal to negative log. And this is what they gave us, right? They wrote it in scientific notation. What does that negative 5 exponent mean? Yeah, you're going to move the decimal that many times. So how many zeros would I have to put in front? 4, right? Because I got to move the decimal 1 time to get it in front of the 2, and then 4 zeros. Okay. So I'd have 1, 2, 3, 4 zeros, 0.23. Okay. And in this case, everything's already on one side of the equation, right? So I just have to type negative log base 10 of 0.000023 in our calculator. And what do we get there? Is it 638?
Yep.
Yeah, okay. All right. Then part B says same formula, but this time we know that the pH is 5.7. So this time I have something for this side of the equation. I got 5.7 equals negative log, and then we'll have our brackets with our hydrogen in it. Okay, so now I do want to rewrite it as an exponential. Remember, having this negative in front is like having a -1. So I could divide both sides by -1 to get rid of the negative, right? So then I just have negative 5.7 equals the log. Okay? And now I can rewrite this log as an exponential, right? What would that look like? Right, perfect. So we would just type that in our calculator, right? I believe it gives it to you in scientific notation, yeah. It says to what power? -6? Okay, so in scientific notation, we'd have 1.995 times 10 to the -6, which really as a decimal means 5 extra zeros in front of that, right? So 1, 2, 3, 4, 5, 1,995 moles, right, was the unit. There we go. So really, we're doing the same thing we did on 7.1, but now you're not having to find the intersection because you can always either rewrite your log as an exponential or your exponential as a log so that you have the variable off by itself on one side. All right.